Okay, so now we're going to continue our discussion of cubic spline interpolation and see how you can solve for the coefficients for each of those cubic polynomials on each subinterval. Okay, so again, you have Sj of x, which is equal to aj plus bj x minus xj plus cj x minus xj squared plus dj x minus xj cubed on the interval xj plus 1, right? And then we have S interpolates F, and then S prime sort of is continuous. S double prime is continuous. I'm sorry, I should have said S is continuous, S prime is continuous, and S double prime is continuous. Okay, so I'm going to look at the conditions associated with each of these things. All right, so so we know that S interpolates F, right? So I'm going to write this as Sj at xj equals to F at xj. So Sjxj is just aj, so this implies that aj is equal to F at xj. So we already have all the a's just from the interpolation condition. All right. So the second condition is that S is continuous. So S j plus 1 xj plus 1 is equal to Sj xj plus 1. So this implies that aj plus 1 is equal to aj plus bjh plus cjh squared plus djh cubed. Okay. And this is for, okay, so these are for j equals to 0 to n. This is for j equals to 1 to n minus 1. Okay, so S double prime is continuous implies that S prime j plus 1 xj plus 1 is equal to S prime j at xj plus 1. Okay, so this implies that bj plus 1 is equal to bj plus 2 cj. Okay, I should be careful here, right? This is hj, hj, hj. So I'm not necessarily assuming that each of the intervals have equal length, so I have to have a subscript j as well. 2 cj hj plus 3 dj hj squared. Again, j equals to 1 to n minus 1. And then S double prime is continuous implies that S double prime j plus 1 xj plus 1 is equal to S double prime j xj plus 1, which implies that cj plus 1 is equal to cj plus 3 dj hj. Okay, so anyway, so you get a system of equations. It's like by imposing the condition that you have the interpolation condition and a bunch of continuity assumptions. Okay, so let's break this out into steps. So step 1 is that you get the AJs from the condition that aj is equal to fxj. All right, this is for j equals to 0 to n. And then step 2 is to set up a system of equations involving the c's. Okay, so it turns out that you can use all these equations. It's like to write down, it's like some sort of expression in terms of the CJs. Okay, so you solve the matrix problem for the CJs. Okay, so hj minus 1, cj minus 1 plus 2 hj minus 1 plus hj cj. All right, plus hj cj plus 1 is equal to 3 over hj aj plus 1 minus aj minus 3 over hj minus 1, right, aj minus aj minus 1. Okay, so right, so there are a bunch of unknowns, a, b, c's, and d's, right? So you can see that the d's can be rewritten in terms of the c's with this equation, right? And then you can solve for the b's in terms of the c's, again with some combination of the other equations. So that's basically what's happening right now, is that you're rewriting it in terms of the a's, which you now know. You can write the d's in terms of the c's, all right, and you can write the b's in terms of the a's and the d's. And then you can substitute everything back into one of the other equations to give you this expression here. Okay. So, right. So what you do then is that you can assemble this into some sort of matrix vector equation, and you can sort of see that what's going to happen is that you get a tridiagonal system. So this here is this right hand side, which is expressed in terms of the a's. Okay, so all right, so it's a symmetric positive definite tridiagonal system for the CJs. And the claim is that there is a way to solve this in ON operations. Okay, so I can solve this in big O of n operations. Okay. And the way you do this is by a very special form of LU decomposition, which exploits the fact that you have this tridiagonal structure. So you use sort of LU for tridiagonal systems. In order to have this very, very efficient type of solution. Okay. And normally it's like LU takes n cubed operation, so the fact that you only have this tridiagonal structure to that matrix is extremely important. And I should say that, as we discussed last time, right, you don't actually have enough equations with these 4 conditions to solve for all the coefficients of the sort of cubic spline. There are sort of 2 missing conditions, right? So we have to deal with that. Okay. All right. So anyway, so that's the linear system. It's like for the C's. Let me say how you get the B's and the D's. All right. And you can sort of see the D's just come from this equation, and the B's can be obtained using, say, this equation, where you substituted the expression for D's in terms of the C's. Right? Okay, so so let me write down step 3 first. Maybe I should have left those out here. Okay, but step 3 is as follows: that you compute the BJ's and DJ's. So the BJ is going to be 1 over HJ, AJ plus 1 minus AJ minus HJ over 3, 2 CJ plus CJ plus 1, and then DJ is CJ plus 1 minus CJ divided by 3HJ, and this is J goes from 0 to n minus 1. Okay, all right. So as I said, it's like we needed 2 additional conditions, and if you recall, it's like those 2 conditions came from the boundary conditions. So let me now revisit the issue of boundary conditions and say what additional, what those boundary conditions mean in terms of the constraint equations. Okay. So, so we're revisiting boundary conditions. So there were 3 of them, if you recall, one of which was the clamped or complete cubic spline. And if you recall, it's like that involves prescribing the derivative of the spline at the endpoints. Okay, and in terms of the coefficients, what that does is to add 2 additional equations, which say that 2h0c0 plus h0c1 is equal to 3 over h0a1 minus a0 minus 3 f prime of a, and hn minus 1 cn minus 1 plus 2 hn minus 1 Cn is equal to 3 f prime at b minus 3 over hn minus 1 an minus 1. Okay, so so if you recall, it's like in the tridiagonal system, it's like I drawn lines at the top and the bottom. I can put this in the top row and this in the bottom row, and you will get a tridiagonal system. So this sort of completes that tridiagonal system of equations, and it's what you use again if f prime at a and f prime at b are known. So you use this if f prime of a, f prime of b are known. Okay. The other approach was this free or natural cubic spline. Right. And this corresponds to the second derivative vanishing at the endpoints. Okay, and this corresponds to C0 equals to 0, and Cn is equal to 0. Okay, and again, you can append this into that tridiagonal system which we talked about before. Okay, and then finally, you have the not condition. okay, which is that the third derivative is continuous at x1 and xn minus 1. So that means that the third derivative of s0 at x1 is equal to the third derivative of s1 at x1, which implies that d0 is equal to d1, and then the third derivative at n minus 2 x n minus 1 is equal to the third derivative at n minus 1 x n minus 1, which implies that d n minus 2 equals to d n minus 1. So again, the not or not condition is used if f prime at a and b are unknown. So use this if f prime of a, f prime of b are unknown. Okay, so all right. So what we're going to do next is that what we've done so far is that we've talked about how you can take the equations which define a cubic spline interpolant and express it as in terms of a tridiagonal system involving these c coefficients. Once you have that, you can compute the d's and the b's, and the a's come from just the interpolation condition. So together you can then solve for the cubic spline coefficients, so long as you have some way of solving a linear system involving tridiagonal coefficient matrices. So what we're going to do next is to talk about how to do that tridiagonal solve efficiently. Okay, so let me just stop here for now.